This video covers Part 1 of Section 2.1, Propositional Functions and Quantified Statements. We're going to start by looking at propositional functions. In Chapter 1, we defined a statement or a proposition as a declarative sentence which has a definite truth value. Most sentences which we encounter in mathematics are not statements, however, because they involve one or more variables, with a truth value which depends upon the values of the variables. In this chapter, we consider such sentences, which are called propositional functions. We'll start by looking at an example of some propositional functions. In this example, we want to identify the variables in each of the following sentences and determine values of the variables for which the sentence is true and values for which it is false. First, look at the linear equation 2x plus 1 equals 6. This sentence contains the variable x, which represents a number. When x is equal to 5 halves, the sentence becomes 2 times 5 halves plus 1 equals 6, which is a true statement. When x is any other real number, say x is equal to -4, the sentence becomes 2 times -4 plus 1 equals 6, which is a false statement. Next, we have the double inequality 0 less than or equal to x less than y squared. This contains two variables, x and y, both of which represent numbers. When, for instance, x is equal to 4 and y is equal to -3, the sentence becomes 0 less than or equal to 4 less than -3 squared, which is a true statement. When, for instance, x is equal to 15 and y is equal to 3, the sentence becomes 0 less than or equal to 15 less than 3 squared, which is a false statement. Next, we have the sentence, the function f is continuous on the interval -1 to 1. This sentence contains the variable f, which represents a function. When, for instance, f is defined by f of x equal x squared for all real numbers x, then the sentence becomes, the function f of x equals x squared is continuous on the interval -1 to 1. This is a true statement. On the other hand, when f is the piecewise defined function, f of x equals -1 if x is less than 0, and +1 if x is greater than or equal to 0, then this sentence becomes a false statement. Since this function has a jump at x equals 0, then it is not continuous at x equals 0, and hence not continuous on the interval -1 to 1. And now we have the sentence, the sets a and b have no elements in common. This sentence contains the variables a and b, which both represent sets. When, for instance, a is the set containing elements 1, 2, 3, and b is the set containing elements 5, 6, 7, 8, then the sentence becomes a true statement since these two sets have no elements in common. When a is the set containing 1, 2, 3, 4, and b is the set containing 2, 4, 6, 8, then the sentence becomes a false statement since these sets have both 2 and 4 in common. The sentences in the above example are all examples of propositional functions, which are defined formally as follows. A propositional function, or sometimes called a predicate, is a declarative sentence that contains one or more variables which becomes a statement when specific values are substituted for the variables. The set of values which may be substituted for a variable is called its domain. We usually want to include the variables in the notation for a propositional function. So for instance, the propositional functions above would be denoted 2x plus 1 equals 6 can be written to p of x, 0 less than or equal to x less than y squared can be denoted q of xy, where we've included both variables x and y in the notation. The sentence, the function f is continuous on the interval -1 to 1, can be denoted r of f. In this case, the variable is f. And finally, the sets a and b have no elements in common contains the variables a and b, so we could denote it s of ab. It's important to remember that propositional functions by themselves are neither true nor false. They do, however, assume a definite truth value when specific values are substituted for their variables. For instance, the propositional function p of x, 2x plus 1 equals 6, does not have a definite truth value, so is not a statement. If we substitute x is equal to 5 halves, we obtain p of 5 halves is 2 times 5 halves plus 1 equals 6, which is now a true statement. If we substitute x is equal to negative 7, we obtain p of negative 7 is 2 times negative 7 plus 1 equals 6, which is a false statement. In all cases, when we substitute a specific value from the domain for the variable, we obtain a statement. We can only substitute values for the variables from the domain. So for instance, we cannot substitute a set, such as the set containing 1, 2, 3, or a function like f of x equals x squared, for the variable in the propositional function p of x, 2x plus 1 equals 6. The result will be meaningless with no truth value, so will not be a statement. Note that the variable in a propositional function need not correspond to a number. A variable may represent a number, a function, a set, a point, a vector, or any other type of mathematical object. The domain of a variable in a propositional function may, for instance, be a set of numbers, a set of functions, or a collection of sets. In part A of the above example, the domain may be taken to be the set of real numbers. In part C, the domain may be the set of all real-valued functions defined on the set of real numbers. In some cases, the domain of a variable in a propositional function will be specified along with the propositional function. In many cases, however, the domain is not explicitly specified, but must be surmised from the context of the propositional function. For our next example, consider the propositional function p of n is a prime number, where the domain of the variable n is the set n of natural numbers or positive integers. We use a boldface n to denote the set of natural numbers. We want to determine the statements and their truth values when n is equal to 17 and when n is equal to 21. When we substitute n equals 17, the propositional function becomes the statement p of 17, 17 is a prime number. Since 17 is indeed a prime number, then p of 17 is true. When we substitute n is equal to 21, the propositional function becomes the statement p of 21, 21 is a prime number. Since 21 is not a prime number, then p of 21 is false. For another example, consider the propositional function q of x, 2x squared plus 13x minus 7 equals 0, where the domain of the variable x is the set R of real numbers. We want to determine the statements and their truth values when x is equal to 1/2 and when x is equal to 3. Substituting x is equal to 1/2, the propositional function becomes the statement q of 1/2, 2 times 1/2 squared plus 13 times 1/2 minus 7 equals 0. Calculating the left side, we have 2 times 1/2 squared plus 13 times 1/2 minus 7 is 2 times 1/4 plus 13 halves minus 7, which is 0. So q of 1/2 reduces to 0 equals 0, which means that q of 1/2 is true. Substituting x is equal to 3, the propositional function becomes the statement q of 3, 2 times 3 squared plus 13 times 3 minus 7 equals 0, since the left side is 2 times 3 squared plus 13 times 3 minus 7, which is 18 plus 39 minus 7 equals 50, then q of 3 reduces to 50 equals 0, which means that q of 3 is obviously false. It's important to understand that the propositional function q of x in the preceding example is the entire equation 2x squared plus 13x minus 7 equals 0. Not just the quadratic function 2x squared plus 13x minus 7 appearing on the left side of the equal sign. The quadratic function 2x squared plus 13x minus 7 cannot be a propositional function since it's not a declarative sentence, and furthermore does not have a truth value when we substitute a number for the variable x. If we substitute a number for the variable x, we're just going to obtain a number itself. Next, we want to talk about truth sets. Given a propositional function, we're interested in knowing when it's true and when it's false. So, suppose p of x is a propositional function with variable x which has domain D. The set of all values of x from D for which p of x is true is called the truth set of p of x. For a simple propositional function, one which does not involve any of the logical connectives, the truth set is usually easy to determine and often just involves a restatement of the propositional function itself. For instance, the truth set of the propositional function p of n is a prime number, with domain the set of positive integers, is just the set of all prime numbers. The truth set of r of f, the function f is continuous on the interval -1 to 1, with domain the set of all real-valued functions defined on the set of real numbers, is just the set of such functions which are continuous on the interval -1 to 1. For compound propositional functions, however, determining the truth set is often not as straightforward and requires using the properties of the logical connectives to analyze the propositional function. The truth set of a propositional function may range from the empty set to the entire domain, as we see in the following example. Consider the propositional functions. P of x, x is an odd integer. Q of x is 2x squared plus 13x minus 7 equals 0. And r of x is greater than 0, where the domain of the variable x is the set R of real numbers. We want to determine the truth sets of the following compound propositional functions. First we have p of x and q of x and r of x. According to the definition of and, p of x and q of x and r of x is true if and only if p of x, q of x, and r of x are all true. Since q of x is 2x squared plus 13x minus 7, which factors as 2x minus 1 quantity times x plus 7 quantity equals 0, then q of x is true when x is equal to 1/2 or x is equal to -7, and is false when x is any other real number. We can then check the truth value of the propositional function by considering the cases x is equal to 1/2, x is equal to -7, and x is not equal to 1/2 or -7 separately. When x is equal to 1/2, p of 1/2 is 1/2 is an odd integer. So p of 1/2 is false. Also, r of 1/2 is 1/2 is greater than 0. So r of 1/2 is true. Then the entire propositional function is p of 1/2 and q of 1/2 and r of 1/2, which will be false and true, which is false. When x is equal to -7, p of -7 is -7 is an odd integer, so p of -7 is true. Also, r of -7 is -7 is greater than 0, so r of -7 is false. Then the entire propositional function is p of -7 and q of -7 and r of -7, which is true and false, which again is false. Finally, for any other real number x not equal to 1/2 or -7, q of x is false, which implies p of x and q of x and r of x will be p of x and false and r of x, which will be false regardless of what the truth values for p of x and r of x are. The propositional function is therefore false for all real numbers x, which means that its truth set is the empty set, which is denoted by the symbol shown, a circle with a slash through it. Next, consider the propositional function p of x and q of x. As shown in part A, q of x is true when x is equal to 1/2 or x is equal to -7, and is false when x is any other number. Then, when x is equal to 1/2, this propositional function is p of 1/2 and q of 1/2, which is false and true, which is false. When x is equal to -7, the propositional function is p of -7 and q of -7, which is true and true, which is true. And for any other real number x not equal to 1/2 or -7, q of x is false, which implies p of x and q of x will be p of x and false, which will be false, again regardless of the truth value for p of x. The propositional function is then true when x is equal to -7 and false for all other real numbers, so its truth set is the set containing the single element -7. For our third propositional function, we have q of x implies p of x or r of x. When x is equal to 1/2, the propositional function is q of 1/2 implies p of 1/2 or r of 1/2, which is true implies false or true. Now, false or true is true, so this is true implies true, which is true. When x is equal to -7, the propositional function is q of -7 implies p of -7 or r of -7, which will be true implies true or false. And again, true or false is true, so this is true implies true, which is true. And for any other real number x not equal to 1/2 or -7, q of x is false, which means the propositional function q of x implies p of x or r of x will be false implies p of x or r of x, which is true, since a conditional with a false hypothesis is always true. Therefore, this propositional function is true for all real numbers, so the truth set is the entire domain R of all real numbers.